So let us look at a specific example. So there is a composite slab, and one end of this slab is maintained at no flux condition, that is adiabatic conditions, and the length is specified as 50 millimeters and 20 millimeters. So that's the thickness of the slab, and let's say that the Q dot A and Q dot B are the volumetric generation of heat in these two slabs, and if Ka and Kb are the corresponding conductivities, and if water is flowing outside, okay, water is flowing outside with at a temperature of 30 degrees C, and the heat transport coefficient is 1000 watt per meter square Kelvin. Okay, that's the heat transport coefficient, and you can throw in some numbers. So if the temperatures are specified as T0, T1 and T2, so if Q dot A is 1.5 into 10 power 6 watt per meter cube, and Ka thermal conductivity is given by 75 watt per meter Kelvin, and if Q dot B is 0, which means that there is no heat generation in the second slab, and if conductivity is given by 150 watt per meter Kelvin. Okay. So we need to find the temperatures. So the question is, we need to find the temperatures of these three locations. T0 is at the location where the adiabatic condition is maintained, and T1 is the interface between the two slabs, and T2 is the exterior surface. So how should we proceed? Yeah, write the balance equation for both. But can we do better than that? We know the solutions separately. Of course, we can write the balances and we can find the solutions. Okay. But can we do better than that? So look at the system and intuit what's happening here. What is happening here? So you should not blindly go and write equations all the time. You have to see what the system is doing. Can we do better than that? Can we do in a simpler fashion? Can we solve the problem? So what is happening at this interface? Yeah? Heat flux is same because whatever heat that is being transported from slab A is being transported to slab 2 at that interface. Okay, what is the flux at that interface? So note that this is adiabatic, right? So there is nothing that is leaving on this end. So whatever heat that is being generated should actually be the flux at which the heat is being, the total amount of heat that is generated because of the heat generation term must be transported only in one direction, right? So that's sort of obvious from the way the problem has been defined, but you must intuit these kinds of things. So the total amount of heat that is generated So Q dot A into the volume of this slab A, which is, let's say if this is L1, length L1, we'll put the numbers later. So this is length L1, L1 into A, so that's the total amount of heat that is generated, and if we specify that it's a steady state condition, that's what we've been looking at, that should be equal to the rate at which heat is being transported in slab B, because there is no heat generation there. So whatever comes in here has to go out if the steady state condition has to be maintained, and that should be equal to H into T2 minus T infinity, right? Very simple. So because there is constant heat transfer rate in slab B, because QB dot is 0, the heat transfer rate is constant. Therefore, whatever heat that is actually flowing at this interface, whatever rate at which heat is being flowing from at this interface, excuse me, should be transported at this interface if you have to maintain steady state conditions. Therefore, Q dot into L1 into A should be equal to H into A, right. So that is rate, we are looking at rate, not flux, right. So we know what Q dot A is. So this means Q dot A into L1 should be equal to H into T2 minus T infinity. So we know Q dot A, we know T infinity, we know the heat transfer rate, so we can find out what T2 is, right. And so that will be Q dot A into L1 by H plus T infinity. So if I throw in the numbers, it will be 30 plus 273. Watch the units, okay, I am using SI units, into 10 power 6 multiplied by 50 into 10 power minus 3 divided by 1000. So that is approximately 105 plus 273, so that is 105 degrees C. So that is the temperature T2, okay, is that clear to everyone? How do we find T1? How do we find T1? We know that the heat transfer rate is constant and we can simply write resistance network, right. So we know how to write resistance network. So the simply based on resistance network, T1, T2, and that is given by L2 by K2 into A, right. So that is the resistance network and this is Q, right. So can we find T2 from here? No, QB is 0, there is no heat generation in the second slab. So if there is no heat generation in the second slab, you could actually write the resistance network, right. So how do we solve this? We do not know the area, right. So what do we do? Do we really need the area? So how do we solve? How do we draw the resistance network, correct resistance network to find temperature T1? Area, we know Q equal to H into A, right. So there are two ways of doing it. You know what Q is, you could use this resistance network, or you can draw overall resistance network also. T infinity 1, call it T infinity, and T1. So you can use either of overall network, or you know what Q is and you can find out what the temperature T1 is, okay. So T1 will be, I will just put the numbers, it's very easy to calculate, 115 degrees C. What about T0? How do we calculate T0? How do we calculate T0? Yeah. So we have to use the solution here, we have to write the model. If the model is not given to you, obviously you have to write the model and find the solution, because the resistance concept is not valid for that slab, and therefore we have to write the model equation and find the solution. And so I am not going to rewrite the equations here. So we solved the equation just now. So you can find out that Q dot will be, T naught will be T1 plus Q dot L square by 2 times Ka is equal to 140 degrees. So remember that slab A is nothing but, if you have a slab which is twice the length of L1, right. So that is the problem that we just solved, right. So where at the midpoint you have a adiabatic condition, right. So that is the same problem. So if you find what is the, yes, yeah, sure. So remember that we solved this problem, right, at x equal to 0, minus L and plus L, and if you have a heat generation, we solved this problem and we found the temperature profile, correct, and we know what is the temperature distribution. What we need to know is what is the temperature at this location, right, that is the midpoint. So remember that we also said solving this problem is equivalent to solving half slab starting from x equal to 0 with a adiabatic condition. Why is it adiabatic? Because if you impose a symmetry condition on this where the temperatures on both sides are same, then you have a maxima at the center. So the profile looks like this. So you have a maxima at the center, which means that dt by dx is 0, which is exactly the flux condition, is exactly the flux boundary condition. So this problem here is as good as solving a problem which is twice the size, and if you get the temperature profile, you can find out what is the temperature at the midpoint, and that is what we solved a few moments ago. So once you know the temperature, this is simply given by this expression here, and you will be able to find out. So remember that the solution is given by, I can give you what the solution is. Yes. Where? Yeah, conduction is included in QB. This is the balance at the interface. So all that is generated. So note that the conduction is happening inside the slab, right? So at the boundary, what comes out of the boundary is the total amount of heat that is generated inside the slab. Of course, it comes through conduction. How does heat come here? Because of conduction inside the slab. But we are looking at what happens at that interface. Because there is no heat that is leaving on the other side, everything has to leave through this side, and so whatever comes here should be the total amount of heat that is transported in the second slab, because there is no heat generation in slab B. Clear? So the solution of this equation would simply be Tx is q dot L square by 2k into 1 minus x square by L square plus Ts. So you put x equal to 0, that is what you would get. So Ts is the temperature of the two surfaces, which is same, and that is nothing but T1 in our problem here. And so if you put x equal to 0 here, what you get is the solution here. Yes. Where? You don't need to know. You know what Q is. Q is h into A into T2 minus T infinity, so the area will cancel out. The area will cancel out when you actually write it. So it's easy. So you can write, so T1, maybe I'll write it here. For the benefit of everyone, I'll write it here. So what is this? So this is T1 minus T2 divided L2 by Ka, K2A, h into T2 minus T infinity, right? So area will cancel out, and you know what T2 is already, you know what T infinity, so you should be able to find T1. Okay? Any other questions? So, I mean, the take home message of this particular example, the reason why I showed this is, you should not blindly just go and write equations for a given problem. You should first intuit what is happening in the problem. Can I make some estimate about certain quantities without solving the equations? Of course, you can solve the equations and verify them, but can I make some intuitive, for example, the intuitive judgment we made about heat transport in second slab, such kind of judgments is very, very important when you are handling these kinds of engineering problems. So you must always pay attention and give utmost importance to your intuition. Okay. So the next topic that we are going to see is extended surfaces. So I am going to briefly give introduction to that in the next 5 minutes or so, and then we will go deep into it in the next few lectures. So far we said by Newton's law of cooling, we said that Q equal to H A into let us say the surface temperature minus the temperature of the fluid to which the heat is being transported. So let's say it could be a slab like this where the fluid is actually flowing past the slab, and this is the surface temperature and this is the temperature of the fluid. Now the question comes in most of the engineering problems is, how can I increase the total amount of heat transport? What are the ways by which, how to increase? It's a very, very important question. How to increase Q? So the purpose of heat transport is basically to transport heat from one location to another. So the better I can do, the better placed I am, right? So if I can design a system which can transport heat better, then obviously I am much better placed. So if you look at these three quantities here, so if I call this as delta T, okay, some temperature difference, so I can rewrite it as H into A into delta T. So the net heat transfer rate depends upon three quantities, right? One is the heat transport coefficient, the other one is the area of heat transport, and the third one obviously is the temperature difference. So these are the three quantities that needs to be tweaked. So if you want to increase heat transfer rate, you can increase either of them individually or you can increase multiple of them, right? Many of them simultaneously if you are able to increase, then you are going to increase the total amount of heat that is transported, okay. So when we discuss convection, we are going to look at how to play with the heat transport coefficient, what are the methods by which heat transport coefficient can be estimated, and what are the factors on which the heat transfer coefficient depends upon, and how to increase them is what we will see for most of the convection chapter. Okay. So now what we are going to see is how to increase the area of heat transport and thereby increase the net heat transfer rate. So one way to do that is what is called the extended surfaces, or in classical literature it is also called as fins. Okay. So there are several equipments where fins are being placed in order to increase the heat transport. For example, in the radiators in car, where you want to dissipate the heat as soon as possible, which means you need to have a very high heat transport. So in order to increase the net heat transport, you design a system which has very high surface area, and in fact the way it is done is, so the fin sort of looks like this. So they sort of look like this. So you have a base here, okay. So there is a base system which is maintained at a certain temperature. So supposing if the temperature of the base surface is Ts, okay. Now you want to increase the heat transport from the base to the fluid which is circulating around, okay. So there is a fluid which is flowing here, it could be any fluid. In case of car radiators, it is basically air which is being circulated. So you want to maximize the amount of heat that is transported from this surface to the fluid. So the way to increase the heat transfer area is you create a thin protruding surfaces like this, and so you have heat transfer occurring from the upper and the lower part of this protrusion that comes out of the surface. And so you can have many such protrusions, and each of these protrusions is what is called as a fin. So you have now added some extra area for heat transport, and that is how you enhance the net amount of heat that is being transported. Now if you look at it, this is a slightly different problem than what we had dealt with so far. So compare this kind of a structure with the structure that we had dealt with so far. So where the fluid which is flowing is actually at the outer end of the system that you are dealing with, and the flow of heat is actually in the direction perpendicular to that of the fluid flow, right. Unlike here, in this case the conduction is occurring in this direction, while simultaneously there is heat loss from the surfaces, right. So here there is no simultaneous conduction of heat and heat loss from the surface, while in the extended surface you have now introduced a system where there is simultaneous conduction of heat and also loss of heat to the fluid which is surrounding it. So in this sense it is a slightly a different problem, and we are going to see how to account for these kinds of systems. So in fact that answers one of the questions he asked a short while ago. What about heat loss from the system? So here we are going to account for simultaneous loss of heat from the solid which is actually conducting heat in one direction. So this is what we are going to see for the next couple of lectures, and how to quantify heat transfer process and how to find out the net amount of heat that is transferred from these kinds of systems.